We want to continue with the example of conversion of decimal numbers to binary. And we want to look at an example that says obtain the binary equivalent of this decimal number, which is 52.625. And my preferred method for doing this conversion is the method 2 that we introduced in the previous lecture. We just need to know that 52 is less than 64, which is the sixth multiple of 2. Therefore, we highlight multiples of 2 from 1 to 5, which is 2 to the power 1. In fact, we start at 2 to the power 0, 2 to the power 1, 2 to the power 2, power 3, power 4, and 2 to the power 5. Therefore, we know that if we take 52 minus that 2, which is here, we get what? Oh, we have already done this conversion, so I think it will be rather straightforward. So we'll have that 2, we are left with 20, and then we say 20 is bigger than 16, therefore we take 16, which is 2 to the power 4, and we are left with 4, and then we say 4 is represented by 2 to the power 2, and the others remain 0. So what we do next is now to find out how do we convert 0.625 or a fraction into binary. And how we do that, there are two methods again: repeated multiplication by 2, that is method 1, and method 2 is just representing it using the weights of the position of a given symbol. So what if we were to do the multiplication, you can start by multiplying by 2, and then you say this is equals to 0 carry 1, 5 carry 1, 12. The one that you get is the first decimal that you will take from 0. Whatever the whole numbers you get here, they are the ones that start adding them to after the decimal. So we have 0.1. Then once we have added it, you drop it so that you multiply again. You multiply, it becomes 0, 0 carry 1, 5, 0 point, and therefore this 0 becomes the second 0. After the second multiplication, and we do another multiplication, you get 0, 0, 0 carry 1. This becomes our fourth one. So that is method 1, which is that of repeated multiplication. The other method, which is method 2, is just applying weights to the position of the symbols. Remember, we had 0. I can actually indicate it as 0.625. What we know is that the weight of the first symbol to the left of the dot is 10 to the power 0. Therefore, when you cross the dot, it becomes 10 to the power minus 1. The second one becomes 10 to the power, So for us to do this conversion, we just know that the binary numbers that we had 52 here, we have already found that it is represented by 110100. So we won't find a dot after that number. What we know is that this one is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, etc. to the left. So to the right of the decimal, you start with 2 to the power minus 1. You don't start with 2 to the power 0, and you continue with the increment towards the negative side. The other one will be 2 to the power minus 2, 2 to the power minus 3. And I think you go until you find the last number. So what we do is we know that 2 to the power minus 2 is equivalent to 0.5. Of course, that is straightforward. I can just indicate it here. 2 to the power minus 1 is equivalent to 1 over 2, which is equals to 0.5. If we do 2 to the power minus 2 is equivalent to 1 over 2 to the power 2, which is equivalent to 1 over 4, which is equals to 0.25. How we finish this one is we say that now we had we are representing 0.625, and we have already we had 52, we represented it as 110100, and therefore we want to present this other number. So what we are saying is that we have used the method 1, and we have found that the answer was 1. So we got the 0.625 to be equivalent to 0.101 using method 1, which is multiplication by 2. So the other method that we have seen is the one of positional weights. So we have said that after 0.625, which we have said we can represent by 0 in terms, this is now decimal, this is now binary. We say that this is going to be 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. So we say 2 to the power minus 1 is equivalent to 0.5. So you just list your number here and you say 0.65625, you minus 0.5, you get 0.125. Then you say, can the next one be used to represent 0.125? You know, the second one is equivalent to 2 to the power minus 2 is equals to 1 over 4, which is equals to 0.25. This one is bigger than 0.25. Therefore, we say it cannot be used to represent it. And therefore, we say this will be, the second one will be 0. So this was 1 because it's representing our 5. This is 0. And therefore, we ask ourselves, can the other one be used to represent 0.125? And we just do the quick conversion, which is 2 to the power minus 3 is equals to 1 over 2 to the power 3, which is equals to 1 over 8, is equals to 0.125. Therefore, this agrees that this can be used to represent our remainder here fully. And then for that reason, we say that 0.625 is going to be represented by 1, which is 2 to the power minus 1. We have seen 0 for 2 to the power minus 2 because it is bigger than the remainder here, and 1 because this remainder is equivalent to 0.125 that we have seen, which is coming from here. When you minus, you get 0.0. And therefore, we say that 52.625 is going to be represented by this decimal fraction and this portion that we obtained earlier. So the final answer is 52.625 is equivalent to 110.101 in binary numbers. That is our final answer.